Right. Did you get a message saying that the meeting is recorded?
Yes, sir.
All right. Okay.
Yes, sir.
Okay, nice. Okay, let's start with the lecture then. So today's lecture will be focusing on a very important thing about geodata. So I'll because after this you can now start working with geographic data. The first one, we'll be talking about geographic data. What are they and what are the importance of the characteristics of each of those data. And then we'll talk about rasters and vectors. And then we'll talk about this class activity after we talk about the maps and scale. So this is the first law of geography, but it's not the ultimate law or anything. It's not like a Newton's first law or something, but it's good to remember everything is related to everything else, but near things are more related than distant things. So why did I put this here? It's because not to give a wrong message. Don't look at the picture and think about something else. But the idea here is that when things are closer, their influence is higher than the things that are further apart. So in geography or in spatial data science in general, we discuss about things that are affecting other things when they are closer in the close proximity. So for example, the idea here says something like this. Say that there is a pollution happening. So somebody is throwing garbage to a nearby place, say to a road or near a river or something. So because of this pollution point, the closer to that point, you will see more pollutants, right? Because that's the area of influence for that particular point source pollution. So when you are closer to that, you have more pollutants like acids, heavy metals, or other sorts of organic pollutants. Everything is closer to that point. But as you go further apart from that point, the influence of that pollution site is less. So further you are away from that, the lesser the influence is. Now, this little idea, everything is related to everything else, that is true. Because if you think about the total environment, total system, that pollution source is connected to some other cases in the environment as well. So collectively, those point source pollutions will affect large scale. But near things are more related than the distant things. That is, if you have a point closer to you, the effect will be higher. So that is what it says. Now, this is common in almost all spatial analytics problems. If you are trying to understand a buffering solution, if you want to understand the minimum distance problem related to spatial decaying, we call this the decay problems. So all of them are related to the relative distance between items, locations, people, whatever that is interested in. So keep this in mind. Now let's move to geographic data. So geographic data, we can look at geographic data in three aspects. The first one, it's obviously a place. So it has a longitude and a latitude. If you think about location data, you have a longitude, the latitude. So that's a coordinate. And also you can have height data as well. So we call it the place from datum. So you have a height. If you think about Mount Everest, the tip of the Mount Everest has a height, right? So longitude, latitude, and a height. We need to think about a place. And you have a time of your data acquisition, or you are simply acquiring data temporally, like for every other day, or every 14 days, every 10 days, depending on the satellite orientation and the orbit of the satellite. That also varies. And also the resolution of your camera, your video recorder, the time dependent parameters will be there. And then there is something called attribute. So place and time, they are easy to understand because you have latitude, longitude, and uh, height data. So the Z axis, but time also, the time of your recording. Uh, and when it comes to attributes, attributes can be many. So it can be a physical, environmental, social, or economic characteristic. If you remember the agent-based model that I just showed you earlier, in that model, you have the street locations of the points of origin, like where people are getting out. Maybe there's a economic center or shop nearby, so people, or a school nearby, so people are getting out of those places, and there is an importance. So the physical, environmental, social, economic characteristic of a spatial entity is its attribute. So it can be a street address, social security number for a person, or NIC in Sri Lanka. It can be a parcel number, atmospheric pressure, temperature, elevation. In a case of a mountain or something, it can be taken as a place as well as an attribute, because it depends on the datum as well. And then you can think about the class of land use, whether it's an agricultural land, an industrial zone. Then you have the differentiating between agriculture, industry, or residential as well. So these are attributes that that we have associated with a place and a time. And these geographic attributes are classified as nominal, ordinal, interval, ratio, and cyclic. So nominal and ordinal and interval, of course, these are things that you already know from your statistics classes. So you have some nominal data saying that about the name, something that describes the importance of the point or the name of it. And then there are ordinal data, low, high, mid, some sort of a scale that gives you the data. Of course, interval is related to continuous intervals. It can be discrete intervals as well. You are familiar with these things, so I didn't want to explain it further. Ratios and cyclic are also pretty easy to understand. What do you mean by ratio? Ratio is something like comparative measure. Say, if you have a percentage, that's a ratio with respect to a total number, or respect to a certain normalizing factor. So you have a ratio. And in terms of the time, you have cyclic events happening, either bi-weekly or every other day or annually. So you have cyclic events. So these weather events are cyclic. For example, the monsoon period, and this right now we are experiencing something like that. So we have cyclic events every September, every October. We know that there is going to be rain. Every April we expect rain. So like we have a forecast for these cyclic events, and we know that these things are going to happen. So these 5 types of geographic attributes are the ones that basically define most of the phenomena that we are interested in. If it is a retail market problem, nominal and ordinal, interval, ratio, cyclic, all these things can be there. For example, in the winter, during the Christmas for the northern hemisphere, you have Christmas gifts plus the winter clothes. So this is something that goes together. In the southern hemisphere, in Australia, New Zealand, South America, so you have the Christmas comes in not in the winter, it comes in the summer. So you don't expect the summer clothes to be used in the northern hemisphere, but you expect the summer clothes to be used in the southern hemisphere during the Christmas season. So even the foods will vary, because you don't necessarily fancy ice cream stuff in the northern hemisphere during the Christmas, but in the southern hemisphere you enjoy those dairy products or whatever the summer food, like things that gives you cool. So it depends. So if you think in terms of a business problem, these things vary. And also these attributes are very important when you are deciding on some marketing or distribution problem. Now, in terms of the geographic data itself, we can divide them to two groups. The first one is discrete objects, first type, and the second type is continuous field. Now, this example here gives you an imaginary set of data. It's an imaginary table. It contains the ID of a wild elephant, then the sex of the elephant, and the estimated year of birth, date of collar installation. This, if you might not be familiar with the person called, he was a professor, Professor Amit Monindra Dasa. He used to work in the University of Moratua, and he wanted to implement this. It was from the electronics department. He wanted to implement collars, install collars on the elephant's neck, so that we can locate their position, and from that to address the wildlife issue, wild elephant issue in the northern parts and southern parts of Sri Lanka. But unfortunately, he passed away in 2008 or something, I guess, during the war period. The cause is unknown, but he passed away. The cause is said to be pneumonia, but people say that it was an assassination or something. But anyways, so he wanted to do this, and if he did this, this would be something like the data set that we will receive from that experiment or that project. So you have an elephant ID, you have a sex, and then estimated year of birth, and then this collar installation. So for each date, you have installed the collar on this elephant, and you can locate at a given time on a specific date the coordinates of this elephant, right? So if you check these coordinates, these are, I just took them from Udawalawe area, I think. So you can, like this, if you have a set of data temporally varying, then you can actually detect the path of these elephants. So whether they are herding, whether they are moving away from, and their patterns. So if you know the patterns, you can actually identify how to avoid them and also how to preserve their habitat. So discrete objects, in this case, there are several discrete objects. The one is the elephant ID, the sex, because you can't, these are categorical terms. They will be there. It's like one time thing. Represent the geographic world as objects with well-defined boundaries in otherwise empty space. So you have the administrative boundaries. You have the Odawala area, and then you have for example, you have the water boundaries, you have the land boundaries. So all these things are discrete objects because they are defined. If you think about the space itself, the space is not, it doesn't know that these discrete objects exist, but we define these discrete objects on the land itself. And then we have continuous field, represents the real world as a finite number of variables, each one defined at every possible position. And this goes with time as well. So in the case of a continuous field, like in a continuous random variable and discrete random variable. So in the discrete random variable, you have, what they are. So I'm not going to repeat them. Continuous random variable, you know that there's an interval, a defined interval for a given random variable that can or cannot be in that boundary, and the edges of the boundary, like the upper bound and the lower bound, you know that the entire thing about it. So the continuous field behaves more like a continuous variable where you have the intervals, and every possible position means that. So it varies. You record discrete data, for example, the location here it says the time and the date of acquisition, but the elephant is moving. So elephant is continuously moving, but you are recording some possible locations, but still it's a continuous field, right? There will be more complex continuous fields like water catchment area, or movements, the vector fields. So, say for example, the wind patterns. You are familiar with these hurricanes, winds, and the weather events. You have the wind movements. So these are continuous fields with the vector fields, and also they represent how things change with respect to time as well as space. In the case of discrete objects, so imagine you are thinking about a hurricane event. So the discrete object will be the town, or the area, or if it is affecting schools and hospitals. So these hospitals and schools are discrete objects, right? So that's the idea of these two types of geographic data that we see. Right, let's move on. So when it comes to geographic data, so we identified two types. One is discrete and one is continuous. In terms of the data representation and analysis, we have two types of data called rasters and vectors. So in terms of the type of data, like what is the nature of the data, we described the discrete type objects and the continuous fields that we see. So in terms of representation and analysis, those two types will be discussed in terms of raster data and vector data. So when it comes to raster data, notice that you have some pixelate or cell-wise information. So it's a matrix. So you have this is what 6x7 matrix, or I throw jth column, right? So the 7x6, 7x7. Is it 1, 2, 3, 4, 5, 6, 7, 8? So 8x7, 8x7 matrix. I throw jth column. So there are 8 rows and j columns, that is 7 columns. So this each one of these cells represent the number of that position. So there is a position. It can be the center of this pixel or this cell, or maybe a corner point, but still, given this area, say it's a 1 meter by 1 meter area, the same value applies. So the blue color indicates it's water, and the yellow color is the pavement, and then you have the building, like in a video game, like a jigsaw puzzle, Lego, whatever. You can name anything that gives some context to what you want to remember. So in the case of pixel, you have this value. So I keep calling them pixels. So I'll just go and introduce you. The cells are sometimes called pixels. It's easy for me to remember it as pixels because I work with image processing. So pixels are these square brackets, squares. Sorry, not square brackets, squares. So typically raster data. So okay, notice that they are squares, not rectangles. There are places where we find rectangles. It depends on when we discuss about azimuth corrections, or in radar remote sensing, that is way beyond the current discussion. So we have this kind of the pixel data comes from the sensor, but the data accumulation comes as a with a angle. So we have how to say, a projection of a square, projection of a rectangle onto a square. So they will be very complex to discuss at this level. So at this level, just think about a pixel as a square itself, and the information whatever gathered is in the pixel itself. It's a square. So just like a normal photo. So you have a pixel here. Typically, raster data comes from remote sensing satellites, which capture information in this form and send it to ground to be distributed and analyzed. So this particular data acquisition thematic mapper of Landsat has a 30-meter resolution. So 30-meter means one side is 30 meters. So just mentioning one side is enough because it's a square. So 30-meter by 30-meter area. Similarly, raster data can be obtained from sensors mounted on aircraft. So when you travel from an aircraft, if you put a camera underneath the aircraft, you can actually take photos of the ground. So these are very difficult to explain in those days. Maybe in 2000, I was not that old by that time. Maybe 2008, 2007, I was in the school. But those days, 2007, 2008, these people were only using aircrafts, the quadcopters, or the things that are available right now, like drones. Those are not known at that time. So it's aircraft, airborne sensors. When you say airborne sensors, it was just aircraft. But now we have so many airborne sensors like small robots, um, the quadcopters, the drones, so many ways of surveillance and data acquisition. Imagery varies according to the spatial resolution expressed as the length of cell site as measured. So I told you that it's a resolution is 30 meter for Landsat, and depending on the sensor and the mode of acquisition, when you find the data source in their metadata, remember in data wrangling, we talked about the metadata. In the metadata, the resolution is mentioned. And according to the timetable of image captured by the sensor, also the metadata will tell you when the image was captured. So we'll learn about remote sensing in another lecture. So I'll not go into details about that, about satellite remote sensing and image processing. It's a different part of the lecture series. So I'll just keep it intact here. You have a pixel. It is square, and each pixel will contain some information about that area. So this can be both discrete and continuous. So in the case of the representation mentioned here, okay, this particular representation with the legend, with colors, and each pixel having a color and a specific land use. We say land use, water, pavement, bare land, building. This is a discrete representation of the space. Pixel information can be used for continuous representation as well, for continuous data as well, continuous fields as well. Remember that. So don't confuse yourself with the previous one and this one. Raster and vector are the data representation and data analysis type. They are used for those things. The vector object, the discrete objects and the continuous field is basically a representation of data types that you will find, the nature of the data. So we use pixel information to represent continuous fields as well. So don't confuse those two. Raster representation divide the world into arrays of cells and assign attributes to the cells. So attributes, I told you what are they. Now I want to ask you something. What is a better representation, A or B, for this case? So imagine that this is a bare land, the yellow color, the orange, I don't know. That color is the bare land, and this blue color is water. So we can represent this one as A and B in two ways. So in A, you have a single pixel showing this water area, and other pixels showing the bare land. In the B representation, you have some two pixels showing water, and then 2 pixels showing land. Can you tell me which one is accurate? I'll give you 2-3 minutes, so take your time, it's fine. Just can you tell me, send me a message or tell me out loud which representation is better? First of all, tell me whether you understood the problem. So the real world, this one is the real world. You have a water area and a land area. These pixels are just to make sure that you understand where the area is. So imagine that this is a grid. So say that this is 1 kilometer, this is 1 kilometer, 1 kilometer, and 1 kilometer. So this is the real world. And we represent this one as pixels. So A and B are pixel representation. I'm asking what represents the real world better, A or B? So I got two answers saying A. Any other? Okay. Can I know why you say that is A? And why do you, I didn't get any B's. Why do you say it's A? Any idea why do you say B cannot be accurate? Because proportion of land and water is not same in the first picture. Okay, very good. Any other idea? A is better because when looking on left bottom square, it doesn't look even like half of the square. Okay, that's good. B is an overestimation of water. Very good. So, okay, so I think I understand what you are trying to say. Right. So A and B both have their merits, and actually, what you are saying is correct. B is over-representing water. I'll tell you why. And A is, in your logic, what you have said is correct. A is representing water and land use based on the area of their occupation. So, for example, in the case of A, now let's talk about A first. You have the water class and the land class. So water occupies the first like 70% or plus area of the first pixel. So it identifies it as water. So in statistical terms, that's acceptable. In the case of this cell, it's very little water, so bare land. So in both cases, A and B, the bare land has been identified correctly for the, I'd say, top right cell. So this cell is correct. This cell is obviously correct because it's a bare land and bare land has been identified as bare land. The main problem that you highlight lies in this particular pixel, where A has not identified it as a bare land, but B has identified it as a bare land, as water. A has identified it as a bare land, B has identified it as a water class. So in your logic, that says, I think everybody has chosen A. That is when water and bare land percentages are concerned, right? So if it is, somewhere around less than 50%, you have gone with the bare land. Imagine that you, I'm not justifying B. The B, we call it, the B has a special name. We call this central point area interpolation. So central point area interpolation means when we look at the sensor for this pixel, the lower left pixel, you can see that the water, this patch is closer to the center of the pixel, this pixel. So in the area representation mechanism, area representation, the percentage area representation, we only look at the area of the square, and if the water area is lesser than say 50%, for the discussion's sake, then we classify this one as bare land because the major proportion belongs to the bare land. In this case, what happens is if the water class is closer to the center point, or if center points of this pixel overlaps with the water class, we identify it as a water class and put the entire pixel as a water class. Now, there are pros and cons in both cases. Imagine that you are trying to identify a wildfire. Okay, the spread of a wildfire. Can you tell me which one would be more suitable for this, A or B? If you are trying to identify the spread of a wildfire, which one would be better? B. Exactly. Because when you think about the spread of a wildfire, you have to detect it and then act very quickly. So if the wildfire is spreading and you just don't care about that the lower left pixel, it will spread. So you will only consider about the wildfire when more than 50% of the area is totally destroyed. Okay, so depending on the application, actually the representation matters. In the case of particularly in the disasters, both representations are very important. in when we think about the long-term predictions and the macro level understanding, A is important. A is the one that we use, but B has very special and very important uses. So I just wanted to highlight both because when the time comes, you will realize what I say, because some are very difficult to identify, and some emergent phenomena occurs in these kind of very as spots. And if your data analysis or your image processing task does not consider these small emergent phenomena, then at the end the analysis will be correct logically, but you will not find these things in the analysis because you have disregarded the small perturbations or the smaller variations in the model. Okay, so A and B are both important, and A is actually, in terms of this one, A is a better representation. That is true. In terms of area percentage calculations, that is true. We usually use A, but B has several special applications that are very crucial when the time comes. Like in the case of a spreading wildfire, it can be maybe catch some some pollutant, radioactive pollutant or point source pollution. Identifying that one at that earliest instant would be very important. So B's representation is also vital. Okay, so both representations are vital, but I agree with your logic. A is one that we use typically. Right, so from rasters to vectors. Vectors are mathematical representations of the locations. It's actually a mathematical abstractions of the real world. We have points, lines, and polygons with well-defined mathematical constructs. So if you think about a vector, have you learned vector fields by now? Linear algebra, I think you have learned, right? Vector calculus. Have you just to have an idea? Have you learned vector calculus, vector spaces, kernels? What have you learned when you think about vectors? Have you learned vector calculus, linear algebra, vector specifically? Is it that you don't remember or you are not exposed to? No idea of it? No one is responding. Yes, sir, we did vector. Okay, so you did vectors. So vectors are, you have an origin, and then you have XYZ coordinates, so you can go for higher dimensional vectors. Vectors is not always the direction. Vectors can be, so in some spatial analytics problems, vectors contain the attributes as well. So it's not always just the directional stuff, but we use points, lines, and polygons to detect vectors in the spatial context, like vectors itself. But when we move from there to machine learning or deep learning models, the vector will include the attributes as well. So you have the location data, the time data, the attribute as a single vector. So in the case of spatial context, I'm referring to the spatial stuff. You have points, lines, and polygons. So to indicate the distances as well as the directions. So points represent location, X and Y, that's latitudes and longitudes. Lines are the connections between the points. So 2 points, the line draws the shortest path between 2 points. So the line that I have drawn here, the smiley face kind of a thing, this line should have so many points. Even though I have drawn that between 2 destination points, you have to have a direction and only 2 points connect a line. So lines are typically captured as connected points. When points are connected by curves rather than straight lines, the density of connected points increase from improved linear scale. So because you can't have more than 2 like you can't, if you think about a line connects only 2 points. So in order to have this type of a curvature, you need to have more points closer together, and connecting them together, we call it a polyline connection. So then only you can get this curve, and it goes like that. An area is captured as a series of points or vertices connected by straight lines. the straight edges between vertices explain why areas in vector representation are often called polygons. So point lines are polygons. Points have the attributes of a location, x and y coordinates, latitude or longitudes. Lines have direction, length and direction, extra attributes, and polygons have areas. And there will be positive and negative areas depending on the vector field that you are looking at. So please remember those stuff. So polygons, when you to the right hand side, you have if you are moving to a direction, and to the right side you have a positive area, and then to the negative to the left hand side you have a negative area. So there are some attributes or some operations of vectors that extend towards polygons as well. So understand each type of vector and raster data and their characteristics. So raster and vectors issues, and this is kind of a comparison. This is not the comparison. It's just a little explanation about different stuff. So issue, volume of data, raster depends on cell size. So if you have a larger cell size, for example, there are satellite names. So I'm using one satellite called MODIS. MODIS has a 25 kilometers in resolution. So if MODIS goes over University of Moratuwa, it's very rare that the whole, we will get some blocks of the university depending on the pixel points. Now remember the A and B representation, right? So in the A representation, if the pixel points lie in, say, half of the university in some cases, we will see the University of Moratuwa in 2 pixels, but rarely that happens. But it depends on the actual orbit of the orbit of the satellite. But if it is a 25 kilometer resolution, usually the whole University of Moratuwa will be included in 1 pixel, and we can't even identify it as the university. It's just single pixel with some continuous bit data, some information about that area. But if we go with QuickBird, the QuickBird goes to 1.5 meter resolution. So you can properly map or properly identify the area. So, but the downside of that is there will be a larger data size. So depends on the cell size. Larger resolutions, or rather, larger pixel sizes, say 25 kilometer pixel sizes, for example, will be giving you lesser image size for the same area, as opposed to a higher resolution image of the same area, because there are so many cells available in a high resolution image. So that's the difference between the raster sizes of the raster, depends on the cell size. In the vector representation, depends on density of vertices. So number of points. I told you that this smiley face type of thing that I have drawn, you should have so many points connecting closer to each other to give a smooth, nice curve. So if you don't have enough points, then you can't have that density. So when you have more points, the volume of the data is large. It's very understandable. Sources of the data: remote sensing imagery, social environmental data. So it depends, like these are things to be read. Applications: resources, environmental, social, economic, administrative, vector, software, raster GIS, image processing, vector GIS, automated cartography. And now this thing have changed a lot. This thing has evolved quite a lot. So we use them together sometimes. Raster to vector conversations are there, vector to raster conversations are there. Conversions and conversation both is there, like vector field connecting to the raster and raster communicating with the vector. Transformations, so many things happen nowadays. So we can't really say that this is that and that is that, but still it's there. In the case of raster, resolution is fixed, vector resolution is variable. So if you remember the vector spaces, you have a kernel, you have the vector space, the ij vectors to the left side, to the x direction and the y direction. So if I say 5j, you know where this is directed, 0, I plus 5j, it's y direction. So if you have some, you can actually identify where the vector is. So in the vector field, it's a mathematical construct, so it varies depending on the resolution, or rather the density, point density of it, to which extent you can identify the distances or calculate the distances or the directions. It varies. However, vectors, because they have mathematical construct, depending on the continuous nature of the function, you can actually go for infinite type of information extraction, because the mathematics is there. But we advise that vector representations are highly abstract. So they are mathematical constructs. Therefore, it's not the actual thing. You are representing, like if you are trying to draw a face, what do you draw? You draw a circle and then maybe two circles for the eyes and then nose and just the mouth. You don't go and describe each and every feature in a drawing like that. So vector representation is like that. You have the real world, you make it abstract. So the roads are lines, the locations are points, or you can go for polygons. The river is not, when we draw a river in a vector field, using the vector notation, it's just you draw a line or with a buffering size, but actual river will vary, right? So it depends. It depends with a lot of parameters. So the good thing is discrete objects lend themselves naturally to representations as points, lines, or polygons. That's pretty straightforward, because if it is a high, low, mid range problem, ordinal data problem, discrete problem, you can actually use colors for changing, and then you can use points, lines, and polygons to show the nominal data. If you go with the school, university, hospital, then you can just put points there, and then you can easily represent discrete objects like that. But there are things that vary with the continuous database. You have A, B, C, D, E, and F, 6 different points. Read them carefully. I'll give you 5 minutes. Tell me what represents better. So for example, if you want to if you want to represent A, which type of representation would be better? Is it vector or is it raster? I just need an answer like this: A vector, B vector, C raster, D raster, E vector, F vector. I mean, something like that. Just think about it and send me a message. What do you think about each of these things, and what representation would be better for representing each of these cases? A, B, C, D, E, and F. I'll give you 5 minutes. Just put it in the chat, or you can speak out loud. Right, so 5 minutes have passed. So tell me what. Okay, A raster, B vector, C raster, D vector, E vector. Okay. A is raster, variable executed regular space. Okay. B vector, C raster, D vector, E vector. So basically, A and C are rasters, others are vectors, right? So easy to remember. A and C are raster, and B, other stuff are vector, right? So let's see. Right. So A and C are raster, and B, F are vector. That's correct. So I have given you the explanations, right? Variable at each of the grid and regular space sample points is A, and then why each of these are suitable is explained here. I don't think that's very difficult to understand. Depending on the context, you can actually use each representation. So you have, for instance, A is equal space lines, points. There's a little, in the presentation, there's a slight shift here, but usually these are equally spaced grid lines. And the vector method, 1, D uses points, 2, B and E uses polygons. And one uses lines to express a continuous spatial variation of the field in terms of a finite set of vector objects. But unlike the discrete object conceptualization, the objects used to represent a field are not real, but simply artifacts of the representation of. I told you that it's actually a model of the reality. So it depends on how you if how you want to model the reality in the GIS or spatial analytics model. Right. So you have the explanations. Just read them and let's move to this other activity. Otherwise, we will lose time. Maps and scale. So I think you are familiar with the maps and scale. If you, for example, here it's a 1 to 24,000 topographic map. These are all maps. Still they are used because the internet and digital maps are not available in the rural areas. If you are hiking, if you are trying to do a construction elsewhere, if you want to do some project, you still need to have these paper maps, survey maps, paper-based maps, maps printed on papers. So still there is a huge scope for these representations. And a scale, I told you a scale is 1 unit represented in terms of the real units in the field. So this map, if you measure 1 centimeter on the map, then on the field, that is in the real world, that will be equivalent to 24,000 centimeters. So if you measure 1 centimeter, that is equivalent to 24,000 centimeters in the real field. So if you measure something here, and then you want to convert it to the real measurements, you have to multiply it by 24,000. That's the basic idea of the scale. And the thing that varies is actually if you are looking at areas, for example, this may be 1 centimeter by 1 centimeter area, but in reality, that is actually 24,000 by 24,000 centimeters square area. So that is a quite a large variation from what you see here. So maps are used with such idea, and when it comes to the digital representations also, the computers identify these representations based on the data that we have included in the model, and they will do they will do the calculations, rectifications, and everything based on what the information that we have entered. So I told you earlier that GIS is part of GIS relates to human interaction as well. So depending on the data, the accuracy of the data and the precision of the data, your analysis will vary. So that's just a little idea of maps and scale. So I will ask the tutor to do the tutorial this Tuesday, and we'll start with some vector representations, some basic idea about ArcGIS at the beginning. So be present in the tutorial as well. Present and just do the activities. Just get the software downloaded and installed and be ready for that. Right now, I'll go to the classroom activity. Divide your class into 3 groups. Read the reading material provided referring to the 3 subtopics given below. The first one is spatial autocorrelation and scale. The second one is spatial sampling, and the third one is distance decay. So if you look at the reading material, it has these 3 subtopics. So you just need to go to these subtopics in the reading material. So without wasting time, I will, this is 9:23 now. I will create breakout rooms for you to, I'm going to create 3 breakout rooms. Assign, let participant choose room. So create, I'll rename the room 1 as spatial, I'll just say autocorrelation. Yes. And I'll rename the second one as a spatial sampling. Okay, sampling. Yes. And the third one, distance decay. Say decay. Right. Now join these groups and work together in groups. Read the reading material that I have shared. I have sent that as a text message. Oh, sorry, chat message. in the group. I'm going to open all rooms now. Participate. Just go and select rooms. At least 5 participants in a single room. That would be better because we have 7 participants. Join them. You can join them. Go to breakout rooms and join. There are.
Spatial sampling, as you can see in the definition, it selects a sample from geographical distributed target population and then use that sample to infer parameters of the target populations, such as the mean and values at unsampled sites. So when it comes to sampling, we select points from continuous fields, and if that field has been represented by as a mosaic area of aerial objects, so when selecting some of these objects while discarding the others, and there are different sampling techniques used in here. Sandupa will explain what are those.
Yes, there are simple random sampling that taking sampling points randomly from the population, and there can be some errors in simple random sampling. Then we go for stratified sampling. We divided the population to the cells and taking 1 point or 2 points from the cell. Then also there is stratified random sampling. From the cell we randomly select a point, and we have stratified sampling with random variation in grid spacing and cluster sampling. Cluster sampling means it's just like as an example, we have 25 districts in our country. For inference statistic, for understand the whole population, we select randomly 5 districts to analyze the whole country. And we have transect sampling and contour sampling, and that is the spatial sampling according to our observations. Thank you. That's our end of our presentation.
Thank you. Very good. Very good. It includes a lot of information. That's good. So let's go for the third group, distance decay. Can you present?
Sure, sir. So our finding about distance decay is like that's studying the effect of distance along with cultural and spatial interaction. It means what happened to the distance between the 2 points when we increase, when the distance keep increase, what happened to the interactions between 2 points when we keep increasing the distance. So for example, like if we get a supermarket and if we locate it at a particular place, and with the increase of distance, the customers coming to that supermarket will decrease. I mean, the customers far away will avoid that supermarket, something like that. So for this, we are going to use 2 examples for you to give an idea about what distance decay is. So the aircraft example, we'll go through that first. So in here, when a flight is closer to the origin, I mean, closer to the land, the air pollution and the chemicals it is releasing will be like having higher impact towards the pollution. So it's what, and when the flight moves away, I mean, from the origin, when the flights move away, the effect will reduce. So that's one example. And to tell you about the other example, I would like to invite Ranul.
Yeah, so when we take a business center in a business city like Colombo, we can see that the further the range increases, the distance increases between this Colombo city and other cities, the things like building height and population density decreases. So this is another good example of distance decay. This also tells that people, there are preferences that people chooses that depends on this. And we can also take an example of ship pollution. That's another good example, like the air pollution one. So oil spillage, if we take an oil spillage for an example, the damage, the density of the oil spill, and that things like that decreases as the spillage, the distance between the origin point of the spill increases. So that's another a good example. So how is this important? So as Winnie mentioned before, when we are like starting a shop in a city, so it depends. The customers come in, as Winnie mentioned, the customer won't come 100 kilometers, even if it offers like better goods, better prices. So the distance decay impacts on how many customers the shop can attract from like nearby towns, cities. So these things, like we can use this to get a better popular customer base. We can have a like a good business. That's it for our presentation. Thank you.
Right, nice, very nice. So both of them, we learn about the sampling in terms of geostatistics, and when it comes to distance decay, we learn about variograms and how the buffering, different stratifications can give us better informed decisions at the end. So both presentations are very good. Can we go with the autocorrelation group now? Can you share and give your opinion, please? Is there no one from the group who can speak? At least there were 5 group members. At least one can speak. Briefly tell us what this spatial autocorrelation and scale means. So we have the screen here. Now, can somebody from the group speak out about these 3 points?
So
Yes.
can you hear me?
Yes, yes.
So spatial autocorrelation is simply say how well objects are correlated with each nearby object across a spatial area. Mainly there are 3 types of spatial autocorrelations. One is positive autocorrelation, negative autocorrelation, and zero autocorrelation. Positive autocorrelation occurs when many similar values are located near each other. When there are different results are found when near locations, then there is a negative correlation. And also there are some situations where there is no autocorrelation between the near areas. So mainly we identified that from the
Right. So autocorrelation also depends on the scale that you take, right? If it is closer, then the density will be high. And for example, in the case of the world, even 2 countries will have closer points if you look at the scale, right? So,
Yes.
right. Okay, thank you. Now, as you can see, there are so many examples and different levels of geodata processing. So I will talk about the next topics. Particularly now we have started the analytics part. So by now we should be aware of the coordinate systems, coordinates, what is a spatial attribute, and also types of geodata, and what are the applications of these things. And I will take this further now with the analysis and some applications directly related to software and hands-on experience. So we have 2 sessions, the tutorial sessions and the lecture sessions. I hope the tutor will be able to do the tutorial session this week. I'm not usually looking over those things. I'll inform the tutor to do that. But yeah, I'll see what happens. So you guys just download the ArcGIS and be prepared. Also, if you have Anaconda distribution, try to find out how to create environmental variables, environment variables, and then install GeoPandas. That will come later. I've not decided whether I'll go with GeoPandas or R for the analysis. So we will have them just in case. I'm saying that if you want to have some idea, you can go and do these things and check those in detail. But ArcGIS is important, so install that and get ready for the tutorial. And next week, I am planning to do georeferencing and uncertainty. So I'm planning to have this georeferencing part together with the tutorial sessions, hopefully, but I'm not sure because I'm not the one who's going to do that. And with this, we'll start the analysis part. So just read about the things we did up to now and be prepared. Okay, so let's meet next week.